Welcome to this lecture, which is the first of two that apply the theory of the previous lectures to the case of PDO production. This lecture provides the qualitative conceptual thinking, and the next we will elaborate quantitative elements. When starting to design the downstream process for PDO, we first need to take a look at the market side. Which PDO purity is expected or desired by clients? On the internet, you can find detailed product specifications of suppliers. PDO has different applications, but PDO that is currently on the market as polymer building block has per kilogram less than 3 gram impurity, of which less than 0.5 gram is water. We better make sure not to exceed these levels. Besides, purified PDO liquid should be very transparent according to a kind of yellowness index. A yellowish color can originate from heating glucose that leads to degradation molecules that may have series of adjacent double bonds and therefore color. These colored molecules will be relatively large but will be at very low concentrations. After knowing the product specification, we also need to determine the starting point of the DSP. We assume for the moment that the fermenter feedstock is a conventional carbohydrate solution. Our PDO broth will contain mostly water, cells and PDO. It will be contaminated with unconverted substrate and metabolic byproducts. Besides, it will have some inorganic salts due to pH control, buffering or feedstock. Let's return to the fermentation that resulted from week 2. This fermentation produces 165 kilomole PDO per hour. The concentration of PDO in the outflow is high, 3 mole PDO per kilogram, which is 228 gram per kilogram. The cell concentration is also high, with 3.275 mole of biomass per kilogram of broth. According to the biomass composition mentioned in the previous week, this is 88 gram of dry bacteria, which corresponds to 352 grams of wet cells per kilogram. Such extremely high concentrations, resulting from a simplified model calculation, have not been reported in experiments. For now, we will switch to data that resemble those of industrial production. A patent mentions 129 grams per liter PDO and 53.5 gram per liter dry biomass, which is still a lot. Glucose is indeed almost completely consumed. However, glycerol, which is a metabolic intermediate, remains to a significant extent. Metabolic side products such as acetate are not reported, but might be present as well. We estimate about 1 gram acetate per kilogram. From the same patent, one can derive that about 6 grams of inorganics has been added per final liter of broth. If dry biomass contains 8 mass percent inorganics, as mentioned in the previous week, about 4 grams per liter inorganics has been taken up by the produced amount of biomass, just mentioned, and about 2 grams per liter remains in solution. Some yeast extract will also remain unconsumed. Together with some E. coli cells that might lyse, that leads to a range of biopolymers in the broth. We estimate about 1 gram per liter. Moreover, antifoam has been added. Its composition can be checked and it will consist of high boiling organic compounds. Jointly with glycerol, acetate, unconsumed glucose and the citrate buffer used, this will be about 18 grams per liter of other organic impurities. Summarizing, we use the following broth composition. And water is calculated as the balance. All the impurities need to be removed to meet the PDO specifications. The high cell concentration will lead to high viscosity and makes it difficult to process. The next step is to find the physical properties that can be used to separate broth components from each other. Some properties can easily be found. In other cases, we notice that we have not exactly defined our components. In our simplified analysis, glycerol, the most prominent component of the other organics, has been given a known entry in the table. The table confirms that we can remove the cells using a solid-liquid separation. Then, biopolymers might be removed from the remaining components using a size-based separation. Now, inorganics and maybe some organics can be taken out using a charge-based separation. For final purification, the differences in volatilities provide a promising opportunity. Now the process of PDO looks as follows. We start with cell removal, including cell washing. Cell disruption is not necessary. Biopolymers removal requires an extra step early on to prevent fouling of subsequent operations. Then the PDO solution must be cleared from the inorganic components and from the main contaminant, which is water. Finally, it is purified from its most similar contaminants, the other organics. Formulation is not discussed because pure PDO will be stable during storage and can be used as such. We will assume that PDO will be produced as a very transparent liquid. Let us now explore the options per step. For achieving step A, microbial cells sediment too slow for a simple gravity settler. Reasonable alternatives are centrifugation, filtration and microfiltration using a membrane. Our first selection is microfiltration. The stream with the separated cells will contain quite a bit of extracellular and intercellular liquid with dissolved PDO. This needs to be recovered by washing of the cells, for instance in a countercurrent setup of diafiltration membrane units. Step B is biopolymers removal. Extraction and evaporation are no serious options. Can you guess why? For biopolymers precipitation and crystallization, the biopolymers seem too diverse and their concentrations seem too low. Adsorption and chromatography are related technologies using a solid phase with affinity for specific components. Size exclusion from the solid phase pores could be a useful mechanism. Membrane processes can also separate on size. Patents describe ultrafiltration membranes with a cutoff of 5,000 grams per mole that may retain biopolymers from clarified PDO broth. For now, we select membrane processes. Inorganics are usually salts remaining from feedstock contamination or from the fermentation medium or resulting from pH control in the bioreactor. In general, salts lead to scaling and corrosion in equipment in high temperature units such as used further downstream. Ion exchange is generally favored to remove salts. In ion exchange, cations are adsorbed in exchange for protons and anions in exchange for hydroxide ions. But precipitation, crystallization and membranes can work as well. Water is one of the most abundant molecules. Reducing water significantly reduces the size of DSP equipment. Although many techniques can be used, the common choice is evaporation if water is the most volatile species. The last step is the removal of small organic molecules that were not yet removed because of physical properties resembling those of PDO. Removing them requires more effort. We must employ sometimes rather small differences in polarity, solubility or boiling point. In the case of PDO, separation based on volatility is a common choice and a cascade of distillation columns is frequently described. To put this all together, see you in the next lecture.